Welcome back to Algebra 2. We're going to switch back, going back to Chapter 6 now. We're going to take a look at exponential growth and decay and some of the techniques that we can use to actually calculate better with them. If we take a look at a couple different equations, we should always be able to make a t-table. At x is -1, we could number crunch. At x is 0, x is 1, and x is 2, and we can see that that is a linear model. The second two are examples of exponential growth. In exponential growth, we plug this into the exponent. 2 to the -1 power is 1/2. It's not a negative number. 2 to the 0 power is 1. 2 to the first power is 2. And 2 to the second power is 4. So these things double every time. When I look at this one and I plug in a -1, that's going to make this 1/3 multiplied by 2, so this is 2/3. Again, not a zero, not a negative number. When I plug in 0, I get just the number that's in front. Plugging in 1, I would get 6 because it is 3 to the first power, not 2 times 3 then to the first power. You've got to remember PEMDAS. Then when we plug in 2, we get 18. So these numbers are tripling every time. These last two are examples of exponential growth. And we are going to also look at exponential decay and use those in some examples of things that really do happen. Exponential growth. The graph will always look like this, and it will not cross the x-axis ever unless we start shifting the graph up or down. This is called an asymptote again. I approach it, I never cross it. You cross it, you're drawing it wrong. The 2 points that I definitely want to see on my graph are 0, 1, and 1, whatever b is. b is the base. It's the number that I take to the power x. And in all of these cases, for exponential growth, b has to be greater than 1, or it wouldn't be growth. The domain of these is all real numbers, but the range is everything above 0, not including 0. Exponential decay is very similar. The difference is we reflected the graph. In this case, b has to be between 0 and 1. b is never a negative number. These 2 points are going to be at 0, 1 and 1b, same 2 points. The graph will approach but never cross the x-axis. And the range and domain are the same. Range, y is greater than 0. The way that we tell whether they're exponential growth or decay is simply by looking at what b is. If b is larger than 1, it is growth. And I can always graph the point 0, 1, and 1, whatever b is. And my graph starts out very, very shallow and gets steeper and steeper. In my second example, this is decay. The reason we know it's decay, what's the value of b? b is between 0 and 1, it's decay. I would know that if I just graphed my 2 points. My first point is at 0, 1, and over at 1, I'm going up 1/2. The rest of the graph gets steeper here and approaches but never crosses 0. I expect to see those 2 points. I expect to see the general shape of the graph. So this is going to be growth. And all I have to do is plug those 2 points. 1, 2, 4. So this graph is going to get steeper faster. Missed. If I graph my 2 points first, those points are going to show me whether it's growth or decay. And the only thing that happens is the graph will get shallower or steeper. So I have growth, I have decay, and I have decay. There's a lot of real-world examples of this. There's depreciation. Depreciation is how much your value of your vehicle decreases as time goes by. I have a number in here that's going to be less than 1. That means it is a decay model. The percent increase or decrease is not the value for B. It is how far away B is from 1. So in this case, I'm going to do 1 minus 0.58, and that is 0.15. To change that to percent, I'm going to multiply by 100. So my annual percent decrease is 15. So I do need to say that it's a decrease. It's the distance away from 1. That's telling me how much I'm going up or down every year. Now, how can I tell when a car is going to get to some value? $8,000. So if this is the original equation, the 8,000 goes here. The original equation was in thousands. This has to be also written in thousands. What kind of methods do we have to try to solve a problem like that? I can move the 25, but I have a real weird problem with that x. This. And now what do? How do I get the x out of there? One of the possible ways that I can solve a problem like this is I can separate the equation into 2 different equations. y1 is going to be the first side of the problem, and I'm going to keep writing it as a fraction, just so it's simpler. And y2 is going to be the second side. So if I graph those 2 things on the same graph, so remember that we do have graphing technology and we can use it. So if we take a look at plugging in our equations, and there's an 8 hiding in the cursor here, we can plug in our 2 equations, 8 divided by 25 and 0.85 to the power x. And if we just graph those in a standard window, I'm not sure what I'm seeing. So we do have to improve our window. And what I'm going to change the window to is I'm going to start with the decimal windows. So I'm going to keep these guys. But instead of having it negative 4.7 but positive 4.7, I'm going to go from 0 to 9.4. And when I graph that, I actually can see it graphing above and graphing below. So I do know I have the intersection, and we calculated the intersection. That seems doable, but there's probably a simpler way. Let's take a look at another problem. In the year 2000, the world population was 6.09 billion. The next 13 years, the world's population increased by 1.18%. We have to convert that to a decimal. And we want to find the population in 2005. So we want to start with an equation. And in that equation, we need to start, and I'm going to type it out so it's easier for you guys to see. We have the starting amount times our rate is going to be 1 plus a rate, not a percent, to the power x. So that ends up becoming 1.0118 to the power x. And we very often don't plug in the actual year, we plug in how many years since the starting point. So in this case, we have 5 years past 2000. So we're going to put in a 5 and number crunch that. Calculator screen right here for that. So how else could we estimate when the population would reach 7 billion? There's a couple different methods, and what I'm going to do is I'm going to take this answer that I already have, and I'm going to multiply it by another 1.0118. So we're going to plug that in, 1 times 1.0118, 2006. Now there's a nice little trick that a lot of calculators do. This is 2006. Hit enter again. 2007, 2008, 2009, 2010, 2011, 2012. The calculator took my last thing that I said to do, which said take the answer, multiply by 1.0118, and it just kept doing that for me. So I can set up the calculator so that it will do that. The year was 2012 because I kept track of it. As I was hitting enter, I went, this is 2006, 2007. That's a really important part of this. So that's another method that we can get there and estimate when we would get to a different value. What if the value of the car was decreasing by 10%? So in this case, the actual annual percentage decrease is 1 minus 0.09 times 100. So the decay is 10% decay, right? That's called depreciation. And what we're going to do is set this up again. So we have 8 equals 25. XT, they're both fine. So can we try to set this up the way that we were doing it? So in this case, we're going to start with 25 times 0.9. That's 1 year. And we're going to multiply this. See how it says answer times 0.9. This is year 2, year 3, year 4, year 5, year 6, year 7, year 8, year 9, year 10, year 11. So before year 11, until we find out what logarithms are. In 1968, the word population was somewhat different, 3.5 billion, and it had a growth rate of 2.09%. Estimate what the current population rate would be if the growth rate had not slowed. What would this look like? Our equation needs to start with, what was our starting point? 3.551. So we're going to write it in billions. And what is our growth rate going to be? We need to do 1 plus the growth rate. And the growth rate needs to be a decimal, which means I need to move 2 decimal places. And that's going to be taken to the power t, or x. What number do we plug in? Well, it's currently the year 2020, and this is 1968, so when we subtract those, we are going to get 52 years. So because we know exactly what year we want to go to, we're just going to plug that into our equation and number crunch it. And what we find is if the growth rate had not slowed, we would now be at 10 billion, not 7.7 billion. Okay, so there's different ways that we can calculate things that are going in exponential growth. So let's take a look at a problem of decay. Radioactive decay is quite common, and we have something called a half-life. In this case, it is referring to days, and the half-life of this material is 28 days. That's where this 28 comes from. And we have 0.5, the amount of time that it takes for half to become non-radioactive is referred to as a half-life. A is an initial amount, and they're not giving me an initial amount. I'm going to make one up. And I'm looking for the percent of chromium, 51, that decays in 1 day. I don't care if it's day 1 to day 2, day 2 to day 3, day 5 to day 6. And I don't care what the initial amount is, so I'm going to plug in 100, the initial amount, and I'm going to do day 1 to day 2. So we plug those things in, number crunch them, and we get these two values. But I want to know the percent that it's going down each day. So what I can do is I can calculate the percent change. We've seen this equation before. Percent change is new minus old divided by the old times 100 to convert to percent. And if I keep track of negative or positive, I'll know if it's going down, decaying, percent decrease, or percent increase. Plugging my numbers in, number crunching, make sure that you do the numerator first. And I have a negative 2.36, which is a decay rate of 2.36%. Next, we have a very common equation. This deals with money. Putting money in the bank, having something called compound interest. We prefer that interest to be in something more frequently than once per year. So this N is going to allow me to determine how many times a year is this calculated. We can have daily compound interest, weekly, monthly, biannually, quarterly, all kinds of different numbers. Our A is our final amount. P is called the principal or the initial amount. We always have 1 plus the rate has to be divided by how many times per year. So this ends up looking like a super small number, but when we compound the interest, we're actually going to get a better rate. So this ends up being the number of times per year times the number of years. So this equation, write it down, make sure you know what everything is. We will be using this. If we deposit $9,000 into account, the account pays 1.46% annual interest rate. We want to find the balance after 3 years. It's compounded quarterly. So quarterly is 4. We plug the 4 in here. And we're going to number crunch this. And in 4 years, an even very small amount of interest, this would end up being 9,402.21. So in 3 years, you've made $400 by letting your money sit there. In an account that makes almost nothing. Okay, for your assignment, I will be putting it on Google Classroom with the book. If you have questions, on Tuesday we will be meeting at 1 p.m. to see what other questions you'll have for the assignments for this week. And have a good day.